Okay, so we were discussing about how to implement this, and we said that we need not only the joints, but also the positions. That's xi, yi for each one of these joints. For the elements, we need the number, of course, and then we need the connectivity table. That means that for every element, let's call it element I, okay, we need the two joints which define that element. For example, let's call it joint J and joint K. So these are joints, okay? What other information do we need for this element? Anybody? What other information do we need for this element?
Longitudinal area.
Okay, so we need area, sectional area. So we need, let's call it sectional properties. So we need inertia, and that's for each one of these, and also the area, the sectional area for each one of the elements. What else? Mechanical properties, people?
Young
modulus for each one of them, because it's possible that in some part you can have a different element than in the others. So we could include that difference. And is that all for the element? Yes, because if we know the two joints, we can calculate the length, and because we know the position of the joints. And also, with the position of the joint, we can calculate the theta angle. So we don't need to input that. Good. Okay, so let's see, let's go on. What else do we need? People, what else do we need?
The external force.
Exactly. Let's go to now to the external forces and okay, so we need the number of external forces. For example, 10 external forces, but each one of those is to be applied in a certain joint, right? And not only that, but each joint, remember, you have deflection in the X, deflection in the Y, and rotation. So as an external force, you could have either force or moment. So we need to specify for each one of them, we need to specify the joint and the degree of freedom. For example, degree of freedom 1 is X direction, 2, and the third is the rotation, the moment, for each one of the joints. So in this case, you could locate this force, this value, in the correct position in the equilibrium system. Good. What else? What else do we need? Mr. Ortega, what else do we need? Mr. Ortega?
Yeah.
What else do we need?
The load transformed to every joint?
No, the loads are already here. My suggestion is these values, okay, I'm sorry, this is incomplete. Maybe that's what you were telling me. We need the joint, the degree of freedom, and the value, of course. So you need to say, in this joint, in this direction, and with that value. Yeah, thank you, Mr. Ortega. What else? Ms. Vera, what comes next? What other information do you need?
Yes, doctor. I really don't know because after
No.
the forces, we know.
Okay,
I might
okay.
think it's okay.
Let me go on. No problem, no problem. If you don't remember, that's fine. Mr. Sanchez, what other information do we need? Mr. Sanchez, are you there? No? Mr.
Yes,
Nevares?
sorry,
Okay,
I can
no
remember.
problem. No? Okay, Mr. Nevares, what's next? Mr. Nevares, what's next? No? Ms. Larrea, what's next? What other information do we need?
Good morning, doctor. The boundary conditions.
Exactly. So that's the supports. This is similar to this. So we need to know how many. Okay, and for each one of them, we need to know the joint. We need to know the degree of freedom. Again, 1, 2, 3. For example, you could have a point where you can move in this direction, but you can move in the vertical direction. So you need to specify that. Or, for example, you could have the restriction for the rotation. Okay. There are several ways to include this. And of course, it's similar to this one, the value. Okay. In general, we would think that the support restriction is 0, right? But there are some examples where somebody expresses a certain value for the displacement. And then you have to calculate the force you need to apply in order to get that deflection. So this value could be 0 or could be something different. Okay. Remember, let me go back that, here the reference system is off, is here. Remember here, see, we have a global reference system. That means that here, okay, these forces has to be expressed in the global reference system and in the deflections. Okay, so let's make a comment on that. Okay, for example, about the external forces, these values. Okay, let's suppose that we have, for example, in the bottom of the ship, we have this element like this. Okay, that's our element. And we have, this is the load. Remember, this is P. What are the units of P? What are the units of P, Ms. Gutenberg? Force per unit length, right? Because, and to get this value, what we do is we multiply the pressure times the spacing between frames. So we assume that every frame takes the load in that span, okay? So that's that. Okay, now let me include here, the global reference system. Okay, so what we need to do here is two things. First, we have to take these forces and we have to convert into these concentrated forces. But then here, this value, we have to specify in this reference system. So we have to do next is take these components and express it in this reference system. Okay, these are the values that you have to include in the program. Okay, because these values directly are specified in the global equilibrium equation system of equations. People, are you with me? Question: what happens with the moment, with the external moment? People, tell me, what happens with the external moment? Somebody, how do you transform this? How do you transform?
Carrillo, disculpe, doctor. Is possible P multiplied by length?
No, that's not what I'm asking. I know what the formulation is. What I'm asking is, how do you transform? For example, here I have this value and I have to express as components in the global reference system. I have this vector, but I have to express it in this reference system. How do you transform that?
I think it's not necessary to transform that because it's a field coordinate in the C direction.
Who is your instructor in finite elements?
Dr. Marin.
Yeah, you don't need transformation because it's perpendicular to the plane. So in both reference systems, you're going to have the same value for the moment. So this is the same, and you have to, if you need it, you have to apply it directly in the system. Okay, so that's correspond. So that's what you have to do. Questions about these, people? So this global reference system has to be clearly defined. Usually we take X in the horizontal and Y in the vertical, but there are certain cases when you have to, it's better for you, for some reason, to incline it. And that's your global reference system. Okay, that depends on you, on the case. But usually we take horizontal X, vertical Y. Comments, questions? Ms. Larrea, are you there? Are you with me, Ms. Larrea?
Yes, doctor.
Okay, so now, after we have done that, we can proceed to calculate the global stiffness matrix. Okay, so the global stiffness matrix. Okay, so this is a very large matrix. Here, what I like to do is I would like to identify. So this is not one single row. There are three in this case, okay? And that belongs to a certain joint. For example, in here, I'm showing you 1, 2, 3, 4. In case you have 4 joints in your program, that's the type of matrix that I'm going to complete. Vertically, similarly. Now, in this case, we're working in the plane. We have 3 degrees of freedom. So for every joint, I have to separate this in 3 rows. So I have something like this. So that's the equilibrium in the X direction, in the Y, and the moments. And these columns are multiplied by displacement in X, displacement in Y, and rotation. Okay, so this is joint 1, joint 2, joint 3, joint 4. This is joint 1, 2, 3, and 4. What I do is start by zeroing. Start by zeroing. So what I do is I take all of these matrix and I make it equal to 0. And then what I do is I take one element at a time, calculate its stiffness matrix, and then I take these values and add it to the global. For example, let's suppose we have here one element, right? Since this is an element, I have two joints. This is a 3 by 3. I'm sorry, 6 by 6. There. 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 Let's suppose that this is between elements 4, joints 4 and 2. So this is 4 and 2 for some reason. Okay, that's your table of connectivity. So joint 4 is the first element, is the first joint of this element. And the second joint is joint 2. But this stiffness matrix of this element has to be included in here in the global. So you recognize that this is a position 4 and 4. So that's this position. So we go and we take, let's change color. Let's take blue. Okay, so we take this part, these 9 elements, and we add in here. This is row 4, column 2. So I take these 9 elements. So this is row 4, this is column 2, and you take this to here, etc. Okay, so knowing this value, the number of the joint, of the 2 joints of each element, you can identify the position in the global reference system. Okay, so for example, this here, okay, is going to be, see, you have 3, 6, 9, and this is 10. So this is going to be the number of the joint minus 1 times 3 plus 1. This is something that some of you recognized. So, and I can do that simply with the number of the joint. The vertical, the number of the column, the same thing. The number of the joint minus 1 times 3 plus 1. And then you have this value here. For the other joint, you will identify this point here. So just knowing the number of the joint. Question, people, questions? No? Okay. After we do all of this, okay, after we do all of this, finally, the global stiffness matrix is completed. Okay? We do something similar with the global, I'm sorry, not with the global, with the vector of the external forces. Okay, let me go back. See, we know the joint, we know the degree of freedom, and we know the value. So here, with the joint, let's suppose that I as an example, let's suppose, as an example, let's suppose that I have a force, okay, see, I have a force in the y direction in the joint 3. What's the position of this value in the vertical, in the column of the external forces? What's the position? Mr. Valles, tell me, what's the position of this force, of this value? Join 3 force in the y direction. What's going to be the position?
1.
Nah, come on.
No.
Here. I have the first 3 positions correspond to the joint 1. And I have 3 positions for joint 1. This is for joint 2. This is for joint 3. So you count 3, 6, and this is the y position. So this is position 8. How do you get this 8 value? Mr. Diaz, how do you get this 8 number? Anybody? Anybody, please.
Because it goes force in X, force in Y, and moment. So it's just
Yeah,
one.
but okay,
Then
okay, go on.
Fx and
But
Fy.
my question is, how can you get this number 8? Because this is the 8th position. How do you get this number? Knowing these 2 values, how do you get this number?
I think that the formula with bar but are now multiplied by 3.
Okay, so it's going to be the number of the joint minus 1 times 3, as you said, Mr. Ordóñez, and then since it is the second degree of freedom, you have to add 2. So it's going to be 3 minus 1, that's 2 times 3, that's 6, plus 2. Why 2? Because this is second degree of freedom. Remember, X is the first, Y is the second, and rotation is the third. So if we have a force in the vertical direction in the third joint, that is going to be here in the 8th position of the external force vector. Okay, people? And then we can go on to solve. Let me save. We can proceed to solve. Okay, so solution. Okay, remember that we have this. And this is very important. This is the main diagonal. Very important there. So we know, somebody said that we need the support conditions. So this is data. Okay. Again, let's suppose that joint 4 cannot move in the X direction. So joint 4 in the X direction, that's going to coincide with what degree of freedom? What position in this vector, in this vector? Joint 4, direction X. What's the position of that displacement in this vector? Anybody? 4th joint X direction.
Number 4.
The 10th position.
10 position.
So it's going to be, okay. How do you get it? 10. Who said 10? Who said 10, please? That's correct. But the question is, how did you get it? Who said 10? Please, come on. Don't.
3 multiply the joint minus 1 plus 1.
So it's the number of the joint, that's 4, minus 1, that's 3. So what you are telling me is that if you have this 3 by 3, that's 9. So if you have first, second, third. So if I say 4th joint, So this element here is 4 minus 1 times 3. So this is 9. And then you need to select one of these. So you have to multiply the number of the joint minus 1 times 3. That's this position. And then you have to add the position or the degree of freedom that you have to identify. In this case, this is 10. So this is the element that we need to be worried about. So let's call it, this is big K. Okay, let's call it LL. And we know that this is 10, this is 10. So that's the position that we know that. What do? We set this equal to a large value. What else? We take this and make equal to the large value times the restriction. And we know automatically that the solution will be the value that we obtain. Why? Because this is a large value. So all the other values in this row are very small compared to this one here. The value that I use usually, it's about 1 to the 20. Did anybody use this process in order to solve for the problem 3 in your past homework? What value did you use for this large value? Anybody can comment on that? Anybody? What value did you use? Mr. Galarza, you explained your homework. What value did you use?
I always use 1 to the 25.
Okay, that's that. Now, be careful here because you have to save in memory the original K matrix. Okay, the original. Once you change this, this is not the original. You have to save the original for the next step. Now, you solve this. Usually in Python, you have several modules to solve this system of equations. So you do not need to implement that. Don't give me that, I know. So that's already been in there. So what you need to do is just connect your program with the module, which is somewhere else, and that's it. So then, you multiply K, this is big K, times D. So that's the second step. This is the first step. And then you find the external forces that you need. You have to be careful because in certain points where you have loads, you have to calculate the reactions or probably you have to calculate the reactions at certain points. Well, that's something that we have to do somehow. And then what we do, remember, what we do next is for every element, so we have in this case, we have the displacement. This is D. In the global, we multiply by T. And the result is the displacement in the local reference system. Remember, this is for one element. With the elements, or I'm sorry, with the displacement in the local reference system, we can go on and calculate internal forces. For example, we have, no, let me draw. Let me draw something like this. So I have this element is inclined there. So we know, for example, that this point moves in this direction. That's the displacement that we get here, the second element. And this point also moves in the local x direction and rotates. This joint, for example, let's suppose it moves downward. And let's suppose this point moves to the left and rotates. Now, with this value and the rotation, you can draw the displacement in the x direction. So this is v of x. And knowing this value here and that value here, you can calculate u for this element, for every element. How we do it? Because we know the interpolation. And once you know this, you can calculate, for example, P for this element is going to be what? Anybody remembers what's equal to P? P for this element, people?
Strain multiply area.
And so it's going to be EA over L times D2X minus D1X. And this is D2X, this is D1X, so you can specify the value of the internal force in this element. You have something similar for these two, but these two depend on this and that value, this and that value. Remember, in bending, you need the vertical and rotation. In the in-plane, you need the axial displacement. And in this case, if you, for example, you could try, let me go back. In here, for example, you could input as the property, not only the inertia, but also the sectional modulus. If you include the sectional modulus, the lowest sectional modulus, you could calculate, after calculating the moment, you could calculate the stress in the joints. Okay, if you want. Remember, that's the normal stress in this direction. Okay, that's the normal stress in this direction. Questions, people? Questions? Everything is clear? Okay. If there are no questions, then I'm going to, it's already posted. So this is the next assignment. You will be given something like this. Don't worry. In this case, this is a very complex structure. You're not going to be given something like this because this is a complex structure. But you will be given something a little bit less, but similar. So in this case, for example, let's suppose that I do not consider this part. I take this part out. So you will give in something like this, right? Now, let's remember that this is symmetric. Okay? And according to the calculation, if the load is symmetric, so the ship is floating, only moving or deflecting in the vertical plane, okay? Every frame, okay, will be behaving in a symmetric way with respect to the center line. So we need to consider only half. For example, if I have this, then what we can do is we can include a certain discretization. For example, here you see that there is a longitudinal, very strong longitudinal. So I need one joint here, 2, 3, 4, 5, 6. Probably I need one here and another here. And to represent this, I need this and that. So if I set this as my global reference system, we could analyze this. And can you describe this? Go on, Isaac, are you there?
Yes, doctor.
Okay, this level here, this is the water line.
The dimension is 4 meters.
Oh,
This
that's
is
that's the dimension, but that's not the draft. Okay, but don't worry, Isaac is going to assign to every group a different frame, and you will be specifying the draft. So with the draft, okay, so let's suppose the draft is about here, okay?
Doctor, the draft is 4 meters. So there is a line.
Here, this one here. So this is the draft.
Yeah.
That's the draft. Okay, so here, that's the draft. So probably what it would be important is to, since this is a big difference here in this piece, little piece, there is no load, and here you have load, probably it's a good idea to include one more joint here. And then you take this element, let me draw here. There, that's the variation in load. And we're going to learn in this chapter how to transform this into this and that. And then you have to take these values and express this in this reference system. Okay, so we have a force in X, a force in Y, and also moments. Questions, people?
Doctor.
Yeah.
For each, I listen for each group, just one analyze one frame, one parent.
Yeah. Every group will have a different frame. And we're going to analyze Engineer Isaac's design. Then let's see how good he was in designing this thing. Okay, and if I include, for example, the whole structure, okay, you can do it, but you can see that the number of joints is going to increase too much. So if I give you something like this, that will be enough. That will be enough. So everybody will have a different frame. Now, in here, of course, this point here, in the same way as we did in the homework, we can assume that this point cannot move because the longitudinal element is very strong. So that point cannot move, can rotate, but cannot move either in X or Y direction. Okay, now to calculate the inertia, okay, let me try to draw here. See, this is the plate, okay? This is the plate. And here we have the frame that we want to analyze. Let's suppose it's a flat bar. Okay, so this is the spacing. This is the spacing between frames. Please, Isaac, try to remember that you have to specify this number. And then here, okay, you have plate and you have plate. It's something like this. And then you can calculate area. Remember, that's what something that we said what we need, and inertia. In that case, it's a good idea if you include also the sectional modulus. So after you calculate the bending moment, you can finally calculate stress. Groups. In the groups, we have 10 female students in this class. So there can be no groups where you have more than one female, because I would like to produce some diversity in each group. And also we have more than, I think it's 13 or 14 people who are from outside the Guayaquil city. So we have to have at least one person, okay, from outside in every group. And in 10 groups, we have to have one woman. And the other two, well, we have to accept that we have no enough females, and there will be all male groups or teams. We are not going to accept anything different than that, because I want diversity in the groups. I am not going to organize the groups. You organize the groups. But I need to include diversity. That's why I'm forcing this. Questions about this? Questions?
So how many people per group is recommended?
Three. That's a good question, 3. So we're going to have 13 groups, okay? This work is going to be controlled, its process, its progress. So next Monday, we're going to have a progress control. And the next Monday, we're going to have another control. So I don't want you to let everything for the last minute. And I'm going to meet in Zoom, in the weekend break in the groups, so we can set a special room for every group. And I'm going to go there and talk to every group to try to determine who is not working. Okay? The report is going to be presented in the day of the second evaluation. I'm sorry, the first evaluation. That's the 8th week of this semester. Oral presentations, 10-minute presentation, and then we're going to have questions. Any comment on that? Please, as soon as you select your teammates, communicate that to Engineer Isaac. So he will assign you a group number. No questions? Okay, people. This Thursday, I would like to do the first check. What have you done until Thursday? Because there's no time to waste. You have 2.5 weeks to complete it. That's enough. 3 people, that's enough. But you need to start working now. Good day.
Today we have the office hour.
No. Today, office hours is to Isaac. Isaac, you're gonna have office hours right now?
Yes, yes, doctor.
Yeah. Isaac is going to give you office hours right now. I gave you office hours last night. Sunday night, I was answering questions.
Okay, thank you, doctor.
No problem. So I'm going to stop recording.